Welcome friends to EPG Pathshala lectures on numerical methods. We are now at module 5 and in this module we are going to talk about interpolation with equally spaced nodes. There will be two such modules on equally spaced nodes. First is this one. The learning objective in this module are we are going to talk about forward and backward differences. Then we will be talking about forward difference interpolation formula and backward difference interpolation formula, or you can say polynomial. And this is what we are going to learn in this particular module. As we have already seen, in Lagrange's and Newton's divided difference interpolation methods were fairly general in the sense that there were no any restrictions on interpolating nodes x 0, x 1, x 2, x 3, x n, except that they were required to be distinct. In this module, the interpolating nodes x 0, x 1, x 2, x 3, x n are assumed to be equally spaced and y 0, y 1, y 2, y 3, y n to be the corresponding values of y. This is because many times many processes are observed at regular interval of time. So, if we have got an additional information about the nodes that they are equally spaced, then can we take the advantage of that information and get somewhat simpler formulae for interpolating problems. So, in this case the Newton's divided difference interpolating polynomial takes a simple form and can be expressed in terms of forward and backward differences. So, when the nodes are equally spaced, the Newton's forward divided difference interpolating polynomial takes a simpler form and can be expressed in terms of forward and or backward differences. So, first we will talk about finite differences. So, we will be talking about forward as well as backward differences. So, suppose that n plus 1 data points x I y I for I equal to 0, 1, 2, 3 up to n are given, where x 0, x 1, x 2, x n are equally spaced numbers such that x I is equal to x I minus 1 plus h for I equal to 1 to 3 up to n, and h is nothing but is called the step size. So, at regular interval of h we are making the observations. Also suppose that a function f represents the true relationship between x and y, that is y I is equal to f x I for I equal to 0, 1 to 3 up to n, then in that case the forward difference of f at x with step size h is denoted by delta f at x and is defined as delta f x is equal to f x plus h minus f x. Now, here you can see that x is a common variable and therefore, delta f x can be thought of as a function of x. F is also a function of x, and if we take specific values of x as x I, so for thus for I equal to 0, 1 to 3 up to n minus 1, if I take delta f of x I, if I want to take, then I will get f x at I plus 1, f at x at I plus 1 minus f at x I, that is the forward difference at point x I, or the same thing can be written as delta y I, because f x I is y I and therefore, delta y I equal to y I plus 1 minus y I. So, that will be considered to be our initial definition of the forward difference. Delta can be regarded as a forward difference operator. Why we can regard this as an operator? Because you can see that delta is operating on a function f and resulting into a function delta f. So, given x we have value of f x and corresponding to that x we can also have the value of delta f x, and therefore, we are saying that delta is an operator which transforms function f into delta f. Higher order forward differences if we are now looking at. So, they can be defined subsequently like this. So, delta square f x is operate delta twice. So, delta of delta f of x and that is equal to delta of f of x plus h, because delta f x is f x plus h and minus f x plus h minus f x. So, when you are operating this will be giving you delta f x plus h minus delta f x, and similarly, so that will be equal to what? Delta f x plus h will be f x plus 2 h minus f x plus h, and minus delta f x will give you minus f x plus h plus f x, and therefore, the actual delta square f x will be given by f x plus 2 h minus 2 f x plus h plus f x, and thus we get delta. Similarly, we will get delta square y I will be equal to y I plus 2, because this is y I plus 2 minus 2 y I plus y I for all I equal to 1 to 3 up to n minus 2 will get. In general, for k equal to 2, 3 onwards, we can say that delta k f x is same as delta k minus 1 f at x plus h minus delta k minus 1 f at x. So, as if delta operator is operating on delta k minus 1 f. So, this is your general formula for kth forward difference. For equally spaced nodes as above, the Newton's divided difference f x 0 comma x 1 can be expressed in terms of forward differences as follows. So, we take f x 0 x 1, suppose we take f x 0 x 1, that will be equal to f x 1 minus f x 0 upon x 1 minus x 0, but this the numerator is delta f x 0 and x 1 minus x 0 is nothing but h. And if you take second difference, I will get f x 0 x 1 x 2. So, that will be f x 1 x 2 minus f of x 0 x 1 divided by x 2 minus x 0, but x 2 minus x 0 will be 2 h, and this will be delta f x by f x, this will be delta f x 1 by h, this will be delta f x 0 by h, and therefore, I will get delta square f x 0 by 2 factorial into h square. So, this is what we will be getting. So, this is nothing but delta square f x 0 and delta square f x 0 divided by 2 factorial into h square, that is the value of this difference. And if you continue like this for any k, arbitrary k, I will get f of x 0 to x 1 up to x k. So, first k plus 1 nodes you take, and that is the forward difference of that will be given by. So, this is divided difference. In terms of forward difference we are getting. So, divided difference on first k plus 1 nodes will be given by delta k, that is kth forward difference at x 0 divided by k factorial into h raised to k. So, this formula helps us to convert your Newton divided difference interpolation formula in terms of forward difference interpolation formula, and that is why this conversion from divided differences to forward differences is considered. So, now we discuss about backward differences. So, backward difference of f at x with step size h is denoted by del f x. So, that was delta operator forward difference, here it is del f x, and as defined as del f x is equal to f x minus h. Thus, for I equal to 1 to 3 up to n, if you write del f x I, then it will be f x I minus f x I minus 1. In the forward difference, we are taking forward value minus the current value. In the backward difference, we are taking current value minus the previous value. So, that is the change from the forward difference, or del y I can be written as y I minus 1. Note that del f x I is nothing but delta f of x I minus 1, because here the forward value will be f x I and current value will be f x I minus 1, which is same as del of f x I. So, both these differences have a close relationship with each other like this. Del can be regarded again as a backward difference operator, just as forward difference operator, and on a function f resulting into a function del f. You can take the higher order backward differences exactly in the same manner as the forward differences. So, del square f x will be nothing but del of del f x. So, del operating on del f x, and that will give me del of f x minus del of f x minus h, but del of f x is f x minus h, and del of f x minus h will be nothing but f x minus h minus f x minus 2 h. So, this again minus minus plus it will make it, and so it will be ultimately f x minus 2 of f x minus h minus f x minus 2 h. So, this is what we will be getting, and in terms of y I, if you write, it will be del square y I, which will be equal to y I minus 2 y I minus 1 plus y I minus 2. In general, for k equal to 2, 3 onwards, we will be getting delta k. So, del k f x is equal to del k minus 1 f x, del k minus 1 f x minus h. So, this is general kth order backward difference we can write in terms of k minus 1 order backward differences. For equally spaced nodes now, above the Newton's divided difference. Now, what we are trying to do is we are trying to use this Newton's backward differences to express Newton's divided differences. So, for equally spaced nodes as above, the Newton's divided difference f x 1 comma x 0 can be expressed in terms of backward differences as follows. So, what we are trying to do is, instead of starting with x 1 to x 0, we are, because we are going in the backward direction, we start with the last node and the previous node to that. So, we are considering the divided difference of f of x n on x and x n minus 1 is given by f x n minus f x n minus 1 divided by x n minus x n minus 1, but this is your h and this is nothing but del f x n. So, so divided difference of f over x n and x n minus 1 is given by del f at x n divided by h, and if I take 3 nodes starting from last again, then we will be getting it as f of x n comma x n minus 1 minus f of x n minus 1 upon x n minus 2. This is the definition of divided difference, and from that we can derive that del square f x n by 2 factorial into h square. That is what we will be getting there. And similarly, for k equal to 3, 4 and onwards, I will be getting f of x n to x n minus k. So, you are getting k plus 1 nodes here, and that will be given by del k, that is kth order backward difference at x n divided by k factorial into h raised to k. So, basically this is giving you divided differences in terms of backward differences. Now, we can construct a table corresponding to forward as well as backward differences. In fact, both this can be shown in a separate table, but I am trying to show you in the same table, because the in fact, we have already seen that forward difference at x I minus 1 is same as backward difference at delta f x I. So, if I am trying to find out this, I will be automatically getting this also. So, now we are considering here x 0 f x 0. So, this is your x I values nodes, these are the f x I values, and using these values I am trying to. So, I am trying to generate this. So, del f x 0 if I want to take, it will be f x 1 minus f x 0, but that will be same as del this is delta f x 0, delta f x 0 will be f x 1 minus f x 0, and this will be del f x 1, because del f x 1 is nothing but f x 1 minus previous value. So, that is same as this. So, that is how I get both this parallelly. So, f x 1 f x 2, so that will be giving you delta f x 1 del f x 2, then f x 2 f x 3 together, x 2 x 3 together will give me delta f x 2 and del f x 3 and so on. Similarly, I can do this for delta square f x 0 and del square f x 2. Now, you can see that this changes here x 1, this is x 2, this is x 3 and so on so forth. Here also it changes. Similarly, x 0 will be replaced by x 2 here, x 1 will be replaced by x 3, x n minus 2 will be replaced by x n. So, that is how the relationship continues even for the higher order differences. And finally, I will get delta n f x 0 will be same as del raised to n f x n. So, one is expressing differences in terms at x 0 and other are expressing differences at x n. Now, we are going to use this finite forward and backward differences to generate interpolating polynomials, and interpolating polynomials will be taking our starting point as the Newton's divided difference interpolation formula, and substituting values of the divided differences in terms of forward, we will get forward difference interpolation polynomial, and if we substitute in terms of backward, we will get backward difference interpolation polynomial. So, that is being done in these slides here. So, suppose that n plus 1 data points x I y are given, where they are all equally spaced numbers, such that x I is equal to x I minus 1 plus h. So, with h as a step size for I equal to 1 to 3 up to n, then Newton's divided difference interpolating polynomial over the given nodes x 0, x 1, x 2, x n is given by p x equal to, this is known already, we already derived this in the module 3, f x 0 plus f x 0 x 1 x minus x 0, f x 0 x 1 x 2 x 0 x minus x 0 into x minus x 1 and so on. So, all this, now we are going to replace this divided differences by means of forward differences. So, since the nodes are equally spaced, the divided differences in the above formula are expressed in terms of forward differences using relation 3, and thus the interpolating polynomial reduces to the Newton's forward difference interpolation formula, and that is nothing but p x. You can call it as a formula or you can call it as a polynomial. So, p x is equal to f x 0 plus delta f x 0 by 1 factorial into h into x minus x 0 delta square f x 0 into 2 factorial divided by 2 factorial into h square into x minus x 0 into x minus x 1 and so on, and we will get it last term as delta raised to n f x 0 n fact divided by n factorial into h raised to n into x minus x 0 into x minus x 1 into x minus x n minus 1. So, this is the simple derivation of the Newton's forward difference interpolating polynomial using divided difference interpolating polynomial. This formula now can be also expressed in a concise form by making an appropriate substitution. So, what substitution we are going to make is, we will be calling, will be making some substitution for this kind of ratios here. So, I am expressing this forward difference interpolation formula in the, with specific form, in the specific form. So, p x equal to f x 0 del f x 0 upon 1 factorial. So, this does not change. I am writing this as x minus x 0 by h. This I am del square f x 0 by 2 factorial. Now, I was writing h square here, but I am now writing it as x minus x 0 into h and x minus x 1 into h. So, h is split over all the factors which we were multiplying earlier, and this is separated out, and that gives me an easy representation for this by making a substitution of this kind. So, if I take s as a new variable introduced for x minus x 0 by h, and since x I is equal to x 0 plus I h, one has the clear cut idea that x minus x I by h will be given by s minus I, because x I is equal to this. So, x 0 will be cancelled and we will be getting I h divided by h will be s minus I, it will be. And so, for I equal to 1 to 3 up to n minus 1, this whole ratio will be represented by just an s minus I, factor s minus I. So, thus the p x in terms of s gives us the concise form of Newton's forward difference interpolation formula 7, and that is p x equal to p x 0 plus h s, because I am writing now p x in terms of s. So, from here I will get h s plus x 0 as x. So, this one I will get, and this will be equal to f x 0 plus s into del f x 0 plus s into s minus 1 by 2 factorial into delta square f x 0 and so on, and I will be getting s into s minus 1 and s minus n minus plus 1 by divided by n factorial into delta raised to n f x 0. This you can see from the expression over here. So, this is your s, this is s, this is s minus 1 and so on. This is s minus 1 and this is s minus n plus 1. So, that is how I get the final expression like this. So, this formula gives better estimate for the values of f at a point near to x 0, because this is forward difference interpolation formula. We expect that it should give better results near the beginning, near the starting point x 0. That is what we expect, but we will see at the later stage that that is not going to be so true. We will see that at the later stage while considering the illustrations. Now, Newton's backward difference interpolation formula we are writing exactly in the same manner as we have written on the forward difference interpolation formula. Again we have got this expression. Now, what we are doing is, instead of considering nodes in this order, we are considering the order of the nodes in this manner, x n, x n minus 1 and x 0. And when we are writing nodes in that order, my divided difference interpolation formula becomes p x equal to f of x n. So, now first node is x n. So, I will get f x n plus f of x n into x n minus 1 into bracket x minus x n plus f of x n, x n minus 1, x n minus 2, x minus x n, x minus x n minus 1, and like that I will be getting. And now, I will replace this divided differences in terms of backward differences, and that is readily available, we know that. So, now since the nodes are equally spaced, replacing divided differences by backward differences using relation 6, we will get p x equal to f x n. So, this will be del f x n upon 1 factorial into h into x minus x n plus del square f x n 2 factorial into h square into x minus x n into x minus x n minus 1 plus so on del raised to n f x n n factorial into h raised to n x minus x n into x minus x n minus 1 x minus x 1. So, this is the formula that we get, and again we can carry out the simplification as we have done earlier. So, we can express p x like this, separating out this h, you are putting it on the separate factors like that, and then now taking s as x minus x n by h and observing that x n minus I is equal to x n minus I h. So, one has x minus x n minus I is equal divided by h will be equal to s plus I. So, this is what I will be getting. So, x minus x n minus I will be given by this, because x n minus I is given by this factor. So, we will get now your concise form of notation will be like this. So, thus the p x in terms of s gives the following concise form of Newton's backward divided difference interpolation formula 9, and this form is like this now. So, p x will be equal to p x n plus h s. The reason is we are considering here x minus x n. So, x n on this side. So, s plus h s, x n plus h s will be x. So, that is what I am getting here. Sorry. So, p of x n plus h s, and that is equal to f of x n plus s of del f x n s into s plus 1 upon 2 factorial del square f x n, and like that we will be getting. So, this is a simplified version of the Newton's backward difference interpolation formula. This formula gives better estimate. This is what again believe that this formula gives better estimate for the values of f at the point x nearer to x n, as the formula makes the earliest possible use of data points closest to x, because here you are using x n and quite closely here. So, x n will be used almost in all the term, x n minus 1 will come in this and all the other terms, and so on and so forth, and therefore, it is expected that you may get a better result if you estimate your value of x nearer to n point using this formula. Now, we consider the illustration 1. Again we consider the same function that we were discussing earlier. So, f x is equal to e raised to 2 x into cos 3 x for x belonging to 0 1. Find the approximate value of f 0.1, f 0.5 and f 0.9 using Newton's forward backward difference interpolating polynomial of degree 5. Why we have selected this is 0.1 is nearer to the starting position, nearer to 0, 0.5 is in the middle of the interval, and 0.9 is nearer to end point. So, I want to show, we want to see that what is the effect of this two different interpolating polynomials in estimating these 3 points, these 3 values actually. So, backward difference interpolating polynomials of degree. Now, I am going to do it by backward difference interpolating polynomial of degree 5 over the 6 nodes 0, 0.2, 0.4, 0.6, 0.8 and 1, because I want equally spaced node. So, you can see the difference between the 2 consecutive values of x is always 0.2, and compare them with their actual values. So, we will compare them with their actual values. Actual values we can compute because f x is known. Given the 6 nodes and compute the corresponding function values, and then the forward and backward differences as given in the table 2 are computed. So, first we do that. So, here we are given the nodes, these are the 6 nodes. These values are found from the form of the function f x. So, we get first value will be 1 and another values are computed from the formula for f x. Then we get delta f x I, and which is same as del of f x I. This is delta of f x I minus 1, this is del of f x I. So, for I equal to 1, I will get delta of f x 0, that is this minus this, and that will be something like that, because this will be 0.23126, and which is same as the backward difference at x 1. And likewise, you get this values, then corresponding delta square values will get difference of this 2 as this value, difference of this 2 as this value, and so on and so forth. So, it is relatively easier to compute here forward and backward differences, because in Newton's divided difference you have to divide these differences by differences of the nodes here, nodal values. But in this case you just have to take the differences, and that is how the table is constructed. You can see that if you have got 6 nodes, we will get only one difference of order phi, either forward or backward we are considering. Now, we are using this estimates to compute our values. So, now here in this case your h, that is the incremental value in x, is 0.2. For x is equal to 0.1, we are calculating s. We are going to use the formula in the concise notation. So, we will get s equal to 0.1 minus 0 divided by 0.2, that is equal to 0.5. So, f 0.1 will be given by 1.0 s into this delta f x by 1 factorial, that is what we are going to consider. So, this is your, if you look at this value we are using there. So, this is why first difference is being used here into this s, then the second difference here, second order difference into 0.5, and 1 minus 0.5 is minus 0.5. So, divided by 0.5 minus 1 will be getting, that will be minus 0.5, and that is divided by 2 factorial is 2, and that is how we can compute the remaining terms, and on simplification we will be getting the value as 1.17029977. So, this is what the value of f 0.1 we get using forward difference interpolation formula. Similarly, at 0.5, if I want to do it, only thing what I have to change now is x is 0.5, my s will change. So, s will change to 2.5 and the formula remains same, and therefore, you can see that these coefficients here are same as the previous ones. This one here, then other coefficients also will be similarly, we will be getting this one here, then we will be getting this one here, they are same, but only this factor will change. This is 2.5, this is 2.5 into 2.5 minus 1, that is 1.5 into 0.5. Here we will get only 2 of them, here we will get 3 of them, and so on. So, we will be getting this computation done for f 0.5 and we get value as this. Similarly, we can find f 0.9 in the same manner, and just we have to change the value of s as 4.5 and rest of the things will be as in the earlier cases. Now, we are using backward difference interpolation formula. So, if in the backward difference interpolation formula we have to change the formula and we start with x n and so on and so forth. So, we will be getting x equal to x 0.1 and this will be 0.1 minus 1 we are considering divided by 0.2 and that will give you minus 4.5. Why we are taking 1? Because your last node x n in the table is 1. So, we are getting x minus x n by h, that is the formula for s there. So, we are getting this backward difference interpolation formula for this. So, 0.1 minus 1 divided by 0.5 minus 4.5, and again you substitute in the backward difference interpolation for concise form of the backward difference interpolation formula. It is already done in this PPT here, and you can get the value as 1.17029977. Similarly, we can compute other two values, and actual value of f 0.1 we have calculated like this, f 0.5 and f 0.9 is given by this. This is just by substitution for x equal to 0.1, x equal to 0.5 and x equal to 0.9 in the function formula, function expression. So, table 3 gives me the comparison. So, you can see here your x is given here, f x is given here, forward Newton's forward difference interpolating polynomial that where is values computed by this are given here, values computed by backward difference are given there, then error in the Newton. So, in our illustration 1 we have already computed actual values of f x at 0.1, 0.5, 0.9, then values of by Newton's forward difference interpolating polynomial at these points and backward difference interpolating polynomial. So, these values are already computed in the previous slides, which are listed down here. What I am trying to do is I am trying to find out error by Newton forward difference interpolating polynomial, that is this minus this. So, this minus this gives me error of this order. You can see that the error is quite small. Even error at Newton backward difference interpolating polynomial is also exactly same as the forward difference interpolating polynomial. So, this example, and if you can see the difference between these two expected values is 0. So, that means this illustration shows that even if we are taking 8 digit approximation here, even then you do not get any difference between the estimated values by forward difference or backward difference interpolation formula, and your estimated values are quite close to the function values. So, the table 3 clearly shows that there is no difference up to the 8 decimal places between the estimated values of f 0.1, f 0.5, 0.9 by Newton's forward and Newton's backward difference interpolating polynomial. However, there is an error in actual values and estimated values, which may be due to the fact that we have rounded the values of f x I s to 5 decimal places, f x I and s to 5 decimal places, and the transcendental function, because it is a transcendental function, is approximated by a polynomial function, because our function f x is e raised to 2 x into cos 3 x. So, which is transcendental function and approximated by a polynomial function, and hence that much error can be justified. So, in summary, we can see that in this module we have discussed Newton's forward difference and backward differences. Then we have discussed the relation between the divided differences and equally spaced differences. We have discussed the relationship between the Newton's divided difference and forward difference, Newton's divided difference and backward difference. Then we estimated or found out the backward difference interpolation formula, forward difference interpolation formula, and then we in the illustration we have compared the estimates obtained by these two interpolating polynomial, how they compare with the actual function value and how they compare with each other. So, this is what we have done. In the next module, we will be discussing the computational aspects and error analysis regarding these two interpolating for polynomials or formulas. Thank you.